This is the 3-9 notes for Calculus 1. This section covers the specific derivatives of exponential and logarithmic functions. You'll note that our exponential functions we have already covered in the past. So the derivative of a very specific exponential e to the x is just itself, and the derivative of a generic b to the x is b to the x natural log of b. So as we did a couple times in our previous sections, just remember that the chain rule is always at play here. So if we end up with a function in the exponent of our original function, then we have to make sure we use the chain rule. I'm not going to go over that again because we've already done a ton of problems with those, but that they do throw some problems into the problem set here, just to backtrack a little bit. So one of the things that you learned in pre-calculus was that the inverse of an exponential is a logarithm. So specifically, if you take the inverse of e to the x, then that is always going to be the natural log of x. If you take the inverse of b to the x, the inverse is the log base b of x. So we need to know formulas for finding the derivatives of logarithms as well, and those are actually right here. So it turns out that the derivative of the natural log of x is equal to simply 1 over x. So that is the base derivative for that function. Now, I will tell you that students will start to get a little confused with these derivatives only because in pretty much all the other functions we dealt with, for example, if we have a power like 2x plus 1, 2x squared plus 1 cubed. So the resulting derivative is also going to have a power, right? Times, I think it's going to be 4x. So that basically power to power, right? So what if you have e to the 3x? The derivative is 3e to the 3x. So e to e. So now with the natural log here, the resulting derivative has no natural log in it. So it almost looks weird. But this is something that you have to get used to. Natural log is a very common function for you to have to find the derivative of, not only now, but in future classes, so you have to be aware. Also, if we go to the less popular base log b of x, the derivative is going to be the same 1 over x, but you have to multiply by the natural log of b in the denominator. So to be clear, though, these are only the base derivatives, which means in reality, the variable x is just a placeholder for the inner function, just like it is here. If we want to find let's say, an inner function e to the 3x minus 5, then when we find its derivative, it's again e to the 3x minus 5 times the derivative of the inner function 3. But note, like, this comes along for the ride. So x was always just a placeholder for the inner function. That'll be the same thing here. So you're very rarely just going to have 1 over x. Instead, you're going to have 1 over the inner function in the problem. Okay, so how does that work? Let's look at our first example. So natural log here of x cubed minus 2x. So your instincts right away should be, well, it's not the natural log of just x, which means there's an inner function present right here, and of course that makes our natural log our outer function. So if I need to find the derivative of this big function, I need to first find the derivative of the outer function. The derivative of the natural log is 1 over x, but not entirely. It's the derivative of 1 over the inner function. So 1 over, bring the inner function along for the ride, times the derivative of, let me get rid of this, getting all squishy in here, the derivative of the inner function itself, which is x cubed minus 2x. So this is actually 3x squared minus 2. So when we multiply this out, this goes straight into the numerator times 1, and then the denominator doesn't change. This cannot be simplified, so this is the derivative of the natural log of x cubed minus 2x. Be very familiar with this. If you look in, what's the best way to put this? So, if you look in, let's say on the internet or something, and you're looking around for like shortcuts and things like that, a very popular formula for the natural log of f of x is the derivative of this. So any function that you put in there is f prime of x over f of x. And you can see that that's actually what happens here. So if this is the natural log of f of x, then the derivative is in the top and the regular function's in the denominator, just like this. So we'll talk about that more right down here in a second, but that is a very common shortcut formula for it. So here we go. As I mentioned, there's your shortcut formula. So this allows you to find a bunch of different derivatives, but worth noting that it's not always going to have an inner function. So let's do some examples below here. Okay, so find dy dx. So dy dx, in number 1, we have to find the derivative. So if you look at this, it says secant x natural log of x. Okay, you see two variables here, two different x's. They're coming from two different functions that are being what? Multiplied, which means we need the product rule. We basically set this up as f and g, so we're finding the derivative of secant times the original function natural log plus secant times the derivative of the natural log. Okay, so this is our value. So what do? A lot of times I show you, we do a little bit of a shortcut. Now what's the derivative of secant? You probably haven't seen that in a long time other than random lab and homework problems. The derivative of secant is secant x tangent x. You should know that by heart. If you don't, get on that. What is the derivative of the natural log? Well, there is no inner function, so what's the base derivative of a natural log? It's just 1 over x, which means we can then simplify this by doing secant x tangent x, natural log of x, plus, well, this is going to be secant times 1 over x. So secant goes to the numerator, and we get x in the denominator. So this is the derivative of secant natural log. Okay, so you'll see similar to, I did a problem like this a while back where I did sine 3x, sine cubed x, sine x cubed, sine cubed 3x. I did 4 problems that were all crazy different. Same thing here. You can see that I did like a secant natural log fest. The first one was a product, secant times natural log. The next one, it says, number 2, it's y equals the secant of the natural log. So it's very important that you look at this and know that this is not multiplication. Not in any world in mathematics. This is basically composition. It's the secant of the natural log of x, which means we're dealing with a chain. So if we need to find dy dx, what do? Well, it's going to look a little weird, but basically we have to find the derivative of the outer function. Well, what is the derivative of secant? We already said what that was. It's secant tangent, but you don't write secant tangent because the x's are placeholders for the inner function. So you write secant natural log of x, tangent natural log of x as the derivative. So basically what this is this is f prime of g of x. So it's take the derivative, which is secant x and tangent x, and put g of x, which is this, in for the x's. Then multiply by the derivative of the inner function. So the derivative of the inner function is again just 1 over x. So therefore we can take the entire left side of this, wrong color, the entire left side of this, secant of natural log, tangent of natural log, and we can put it over x, which is going to be our derivative for our problem. So crazy looking stuff, but that's the idea. Now, this is there's a lot of sections where students get tripped up. I'm not going to lie, this is a hard class, but literally this is another area where students, so I would get students that would write secant x tangent x derivative of natural log and end there. You just have to know that the x's are placeholders for the inner functions, and you can't leave that. That's got to be an important concept that you understand. Okay, so how about natural log of secant? So basically, all we did was switch these to go here, which means we've changed the dynamic of the problem. Again, though, it is not multiplication. It is composition. So what do we need to do? Well, we have to take now the derivative of the outer function. So The derivative of the outer function of natural log, again, is 1 over a placeholder for the inner function. So 1 over inner function secant, that comes along for the ride, times the derivative of secant, okay, which is our inner function. So what do? We take this derivative, which we have found several times above, and we get that. So if we write this out, we're going to get, this is going to the numerator, secant tangent, over secant, and something very nice happens. Turns out that these, it's all multiplication, so those cancel, and all of this becomes just tangent x. All right, so again, we have 3 varying problems of the same functions, and then vastly different results for their derivatives for these natural logs. Good practice. Okay, let's do the same type of exercise, but let's do it for generic logarithms, log base b logarithms. Okay, so here, what do we need? We have to find the derivative of log base 5 of x squared minus 3. So clearly, we have an inner function that's inside our outer function log. So what is the base derivative? Well, let's get rid of all this stuff. So the base derivative over here is 1 over x ln b. So remember, though, that the x is a placeholder for the inner function if there is one. If there's not, then you don't have to worry about anything. So here we go. What's the outer function of this chain? It is clearly log base 5. So we have to find the derivative of that. Well, the derivative is always going to be 1 over x ln b, or in other words, the inner function coming along for the ride in place of x, natural log of our base, which is 5, times the derivative of x squared minus 3, our inner function. So we know this is 2x. Therefore, when we do the simplifying, that goes to the numerator, and we get x squared minus 3, natural log of 5. This is your derivative. Very straightforward stuff, as long as you get that x is a placeholder. Okay, so let's do these problems. Again, very similar to our previous exercise. So if you look at this, it says log base 2 of x, cotangent of x. So we're looking at 2 different functions with x that are clearly being multiplied. So again, what are we doing? You're using the product rule. So what does that look like? So we're going to do the derivative of log base 2 of x times cotangent x plus log base 2 of x again times the derivative of cotangent x. Okay, again, we have to go back to our rule. So this is a base log function. So there is no inner function involved, so it's just going to be 1 over x natural log of our base. So in this case, it would be 1 over x natural log of 2. What about cotangent? Another one that you should remember. You might not, but you want to make sure you get into that habit. So how do I remember it? I remember that tangent's derivative secant squared. So that means cotangent's derivative is negative cosecant squared. Okay, that's always how I remember it. I remember it by cofunctions, and then the cofunctions have negative derivatives. So negative cosecant squared. So if we put this all together, it's a very crazy looking derivative. It looks like this here is all denominator work. So cotangent x over x natural log of 2. And then this negative is going to change that sign there to minus log base 2 of x cosecant squared x. Which means this is going to be our derivative for this particular problem. Okay, so similar to before, we don't have a lot of inner functions. We start with one, but we don't have a lot of inner functions. We're just going through the process of understanding the difference between product and chain, basically. This is why I do this exercise, because students are often confused by that. But if you look at 5, again, it looks like we went from a product to a composition, which means we need the chain rule. So what does that look like? So if we're doing the cosine of log base 8 of x, that means this is the outer function. So what's the derivative of cosine? It's a negative sign, but then we need to bring the inner function along for the ride, log base 8 of x. Then we multiply by the derivative of that same inner function, log base 8 of x. So we go to here, we know that this is 1 over x ln base 8 as our derivative. So if we multiply this all out, we're going to get negative sine log base 8 of x all over x natural log of 8. And this is going to be our derivative. If we reverse the process, so if we swap these, right, we're going to get log base, it looks like no base, of cosecant of x. Whenever you have no base, if you recall from pre-calculus, that means that this is a 10. Okay, got to remember that. Any log base nothing there is base 10. So if we do the derivative, now the log is the outer function. So we have to take this derivative here and change it into a chain rule version. So what is that? We do 1 over x is a placeholder for the inner function, which comes along for the ride, natural log of the base times the derivative of that same inner function, cosecant x. All right, so where do we go with that? Oh, and note, didn't realize that my eyes are failing me, but cosine became cosecant. I wanted to do that, but I just forgot. So what does that mean over here? So this guy, what's the derivative of cosecant? Well, if you know that the derivative of secant is secant tangent, then the derivative of cosecant is going to be the negative version of the versions of the previous one. So we're going to get negative cosecant x, cotangent x. And basically, I remember that like this to this day. I learned that in college, like you guys. So this will end up going to the numerator, cosecant x, cotangent x, over cosecant x, natural log of 10. And interestingly enough, these wipe out, and we get negative cotangent of x over the natural log of 10 as our derivative. Okay, so this next part here is a little mini. It's like it's actually kind of separated a little bit from the lesson in the standpoint that it's more of a be on the lookout type part section here. I'm going to read. It says, pay special attention to the presence of variables in the exponential and log equations. Okay, variables. So for example, in exponential, there's a variable. We know the derivative of e to the 2x is 2e to the 2x. We knew that, right? For example, there is a big difference between finding the derivative of e to the 2x and e to the 2. Oh, that's interesting. So basically, they remove the variable. So the question is, if you remove the variable, then what is the derivative? Okay, so this is one of those things you have to think about for a second here. Because if there's no variable, what does the value become? It becomes a constant. So I often do this, like in the homework, I think there's one like this. So I'll be like, hey, what's the derivative of e to the 5? And what do you think students will do? It's e to the 5. No. The derivative of any constant, this is a constant, is 0. Okay, so that might have been a sort of an enlightening moment right there for some to see that, but be very careful with that. Now, the same thing happens with the natural log function. So clearly, we can find the natural log of 100x. The natural log of 100x is basically f prime, which is 100, over, if this is f of x, it's going to be 100 over the original function, 100x, which is just going to be 1 over x. So that's pretty easy, right? But what if I dropped the x and said, what's the natural log of 100? Well, natural log of 100 is a constant, which means that the derivative is again going to be 0. And how do I know it's a constant? Because all I'm doing is taking e, which is a number, to the power 2, and the natural log of something, which is the inverse of an exponential, again, a number, with 100, and you're going to get 0. So just be very aware of these situations right here. They don't come up a lot, but they might get you points here and there on homeworks on labs that I recall. So just be on the lookout for non-variables when it comes to exponential logs. Next, it says another tricky situation for students is the difference between power and exponential functions. Remember that this solely depends on where the variable is located. The following are good examples. So note, I use the pi variable only because I wanted to make it more challenging. For example, look at here. It says find the derivative of x to the pi. So x to any value is a power function, essentially. Squared, cubed, 50, whatever. It's a power function. So x to the pi is a power function. So how do we find the derivative of a power? We bring pi to the front. We just have the same base, and then we subtract 1 from the exponent. So believe it or not, that's my derivative. All right, so that's pretty super simple. What about exponential? Well, the derivative, if you look at the exponential function, now the variable is now in the exponent, and the base is the value. Okay, so pi to the x. Well, you just learned just now what the derivative is for an exponential, not just now, but you learned before. It's b to the x natural log of b. Okay, so let's do that for our problem. So it's going to be rewrite b to the x and then natural log of b. So that's the derivative of the exponential. I do have students that mix these up sometimes. So basically this is, like I said, this is be on the lookout for nasty little exceptions and things, and the difference between derivatives, because they can cause some headache. All right, so the remaining part of this section's notes is all about one topic called logarithmic differentiation. So this is going to be a challenge for students, not because it's hard, but because it's remembering log rules. So before we even get started with anything, let's talk about our log rules. So if you recall from the beginning of pre-calc, if you take the log of a product, it's the same as the sum over here, the sum of their individual logs separated. Just like if you took the log of a quotient, it's the same as the difference of the individual logs. Also, if you have the log base A of x to a power, the power can actually go to the front of the log. These are very generic, basic log rules that you learned in pre-calculus. We are going to need those in order to do what we want to do. Now, logarithmic differentiation can be done in a variety of different ways. There's two major ways to work with it. I particularly work with one method because it helps us with some of the things we're going to do in Calc 2, and the way I do it really helps do that. So, but that doesn't mean that if you looked it up, you could find other ways to do it. But what I do is I purposely introduce something called a tower function as a way to introduce a log differentiation. So what is a tower function? It's this value right here. Y equals x to the x. Okay, so a lot of times that's like mind-blowing for students because literally they have never seen it before. And truthfully, I don't know if I remember seeing it a lot in my college days until later on in math, but this basically, it's sort of a combination of an exponent and a power function, but not really at all. It's variables not only in the base, but also in the exponent. So for example, a power is this, an exponential is this, but this is a tower function, right? So that is basically what we're going to use as a way to utilize and learn logarithmic differentiation. We're going to use properties to find the derivative of a tower function. Okay, so what I'm going to do down here is to the end of the page, I'm going to go through a full sort of structure, a process to find the derivative of any tower function. So the goal is to follow it and be able to give it back to me in the example following this and beyond, homework, labs, exams. So what do? Well, we can't use the derivative of a power or an exponential on a tower function. So what we need to do is be creative here. We need to do something different. So what we do is we take the natural log of both sides of our equation. Okay, the natural log of f of x is equal to the natural log of our tower function x to the x. Okay, so then we go back to our logarithm rule, which is our last one here, and we go, okay, right now we have this generically on the right side of the equation. Now remember, log and natural log are interchangeable. So we basically have that on the right side, which is right here, which means we can take our exponent and move it to the front. So we actually get x natural log of x when we take the exponent and move it over here. So far, so good. This is what we're dealing with. Once we have this, we can then take the derivative of both sides of the equation. Now, when we do the derivative of both sides of the equations, we have to be careful. So first of all, let's do this. So I'm gonna write it out. So the derivative of the natural log of f of x equals the derivative of x natural log of x. Okay. So on the left side, if you recall, this is an example of implicit differentiation. But luckily enough, I gave you a shortcut up here somewhere. Hold on. I gave you a shortcut that you can basically use to avoid implicit differentiation. So the derivative of the natural log of f of x is always going to be f prime over f. So that's what we're going to put on the left side. F prime of x over f of x. On the right side, we have the product rule. So we're going to have the derivative of x, then natural log of x plus x times the derivative of the natural log of x. Okay, we know that this is 1, and we know that this is 1 over x. Okay, therefore, on our final step here, we should be able to, before we move on, we should be able to write the same left side and then natural log. Note that we get x times 1 over x, which is just 1. So far we have this right here as our equation. Okay, so moving on, remember the point of this entire problem is to find the derivative f prime of x of our original function f of x. So if you look at what we have right here, we have f prime of x in the numerator. So it makes sense that we need to isolate f prime of x on the left side of the equation. How do we get rid of the f of x here? We multiply both sides by it, which is going to give us f of x, natural log of x plus 1. So multiply, just to be clear, get rid of these arrows. We're basically multiplying both sides by f of x right here, okay, in order to get this. So when we get this, we go, okay, well, this all came out to be something pretty simple, but how is f of x going to do us any good? Now think about this for a second. Don't we already know what f of x is? Look at our original problem. What is f of x? It's right here. Oh, look at that. It's actually the tower function. So we replace f of x with x to the x. We bring down and copy natural log of x plus 1, and we determine the derivative of our tower function. Okay, so our goal now is to reproduce this in a completely separate example. So I find that when I give this on exams, it doesn't always go that great, mainly because students have so much to study in such a short time. They sometimes let this go, realize there probably is going to be something there, and you want to have the points for it, so make sure you can do it. So what do we need to find? We need to find the derivative of both of these. But note, look where the variables are. There's one in the base, and there's one in the exponent, which means this is identified as a tower function. So as soon as we know that this is a tower function, we can go ahead and find the derivative by using natural logs. So we immediately take the natural log of both sides. As such, what was the point of taking the natural log of both sides? Well, this exponent was actually the problem in the original function that didn't allow us to find any type of derivative. So what do? We just rewrite this, and we move, because of the basic log rules, we're allowed to move this to the front. Now, this has nothing to do with derivatives so far, folks. I know some students are going to look at this and say, oh, 3x to the front, that's a derivative. It isn't. Literally, all we've done so far is basic log rules from pre-calculus. The whole point of it is to get this on the right side of the equation, a product, rather than an exponent to an exponent that are variables that we don't know how to find the derivative of. Once we get this, then we are able to find the derivative of both sides. So we can now take the derivative of both sides of this, and what do we get? Well, the left side, we have a shortcut. It's just f prime over f, always. How do we know that? Because we need it, it's just the chain rule. It's what's the outer function? 1 over x, or 1 over the inner function, times the derivative of the inner function will get you this. So then on the right side, we have to do derivative of 3x times the natural log of 2x plus 3x times the derivative of the natural log of 2x. All right, a little bit of shortcut magic. This is 3. What is this? We have to be very careful. This is another chain rule because there's no longer an x in here. There is a 2x. So how do we do that? What's the outer function? Natural log. So we do 1 over, inner function comes along for the ride, multiplied by the derivative of 2x, which is just 2. So if we look at what we have left over, note that this 1 over 2x times 2 is just 1 over x. So we kind of lucked out with an easy result. So coming up here, so we currently have f prime of x over f of x. On the right side, we have 3 ln 2x plus 3x times 1 over x. Now, if you look at that real quick, 3x times 1 over x is just 3. So we can really just shortcut that process. All right, so what did we do in the last step over here? So once we got here, we needed to multiply both sides by f of x so that we isolated the derivative designation on the left. So we're going to get f of x times 3 ln 2x plus 3. And then once we have our f of x, we can then replace it with our original function 2x to the 3x and get this, bringing it down, and get this as our final derivative. It is a little crazy, but the process is pretty straightforward, and I'm going to show you why I default to this specific process with nothing to do with tower functions. Okay, so when you get into, if you're taking Calculus 2 and beyond, there are times where you get functions that are just absolutely unmanageable to find the derivative of. So, for example, I gave you this one. I had to go over the board here so you understand. So if you look at this function, if we need to find the derivative of this, it is an absolute debacle. Why? The entire function is a quotient, but in the numerator we have a product, and then in both the numerator and denominator we have a chain. So, wow. So this would probably take forever to find the derivative of, going step after step, and the chances that most students will get to the end are not that great given all the little mini errors that you can make, and then everything goes crazy. So, why am I doing this? The idea is we want to use as many of these chain rules and quotient, we want to use as little as possible, right? We don't want to do that. So many errors. So instead, believe it or not, you can use logarithmic differentiation to solve this in an easier manner, believe it or not. So what does that look like? Well, just like we did before, I'm going to take the natural log of both sides of this equation. So again, on the left side, we have the natural log of f of x here. But then why do we do this? Again, let's go back to our rules. All right, so let's go back to these guys right here. So if we have the product, the log of a product, it's the same as the sum of the logs. If we have the log of a quotient, it's the same as the difference of the logs. So if you look at what we have in our problem right here, we have not only a quotient, but we have a product. And whenever we separate logs, we're very easily allowed to separate them into pieces. So we have two expressions in the numerator, so they result in positive logs individually. Positive natural log of 3x minus 2, positive natural log of x plus 1 to the 10th. We have an expression in the denominator, which is going to be a negative log because it's in the denominator. Now, some of you might look at that and your brain explodes. Well, that's because you don't remember what you did in pre-calculus, because you did all of this in that class. Separating, it was called expanding and condensing logarithms, and that's what we're up to when we're doing this. Now, a quick note, remember with radicals don't usually help us, so instead we turn them into exponents, so we get this instead. So just to be clear there. So we can also use our other rule, our other logarithm rule, our last one here, to know that if we have an exponent, we can bring it to the front of any problem. And we happen to have that here. So not in the first one. So we bring this down. But this one, we get 10 natural log of x plus 1. Right? Remember, this is not a derivative. So we're not putting a 9 there or anything. This is just a log rule. Minus, and then remember, this is a half now. So the half comes to the front, and we get natural log of 2x minus 5 after that. Okay, so we've gone to the point where, believe it or not, we just made taking the derivative incredibly easy. Why? Well, if we take the derivative of both sides of this equation, so d dx of all of it, all the way across, right? We know that the left side is always f prime of x over f of x, right? But the right side is straight natural log derivatives. For example, if you look at this guy here, this is, the derivative of natural log is 1 over the inner function times the derivative of the inner function, which is 3. Okay, 3. This one, we're going to have 10, which is going to be a constant that comes along for the ride, just a constant. Then the derivative of the natural log of x plus 1 is 1 over x plus 1 coming along for the ride, times the derivative of x plus 1. Then over here, the 1/2 stays put, so we're going to have 1 over 2. We're going to have times 2x minus 5. Actually, you know what I'm going to do for that? I'm going to make it a little bit easier for you. I'm just going to leave the 1/2 here. Times 1 over the derivative of natural log, 1 over inner function, times the derivative of the inner function, 2x minus 5. And by the way, if it's easier here, if that like blew your mind when I did that, you can do this instead. You can just put the 10 in the front, and then 1 over x minus 1 times the derivative. So if we put all of this together in our problem, this is going to be 3 over 3x minus 2 for our first element. It's going to be, it looks like 10 over x minus 1 for our second, because this is 1. And since this is 2, this 2 and this 2 cancel, and we get just 1 over 2x minus 5. So the only thing left to do is, so remember, f of x is this. Not that. Hold on. F of x is, is this. So all we have to do is put that, when we multiply both sides by f of x, right here, we're going to have an f of x here times this craziness. Which means that the resulting derivative is going to be, when we replace f of x with the original function, here we're going to just copy this all down. Alright, so this is your answer. Now you might, I know a lot of students are going to be like, wait, so this is easier? Believe it or not, it is. This is a train wreck, trying to find the derivative in a regular way. So this is a much preferred method for that. Also be aware that this, we use logarithmic differentiation in all other things in Calc 2 other than finding derivatives that help us determine very easy functions to manage. So this is just a preview. I might give you one of these in the homework. I don't think I'm going to necessarily test you on this per se, but homework labs possibly. It's just, this is something that I want to sort of show you so you have a base of something that you're going to see in the future.